I think I want to jump right in to
Hmm.
discussing, one of the 18 dimensions, temperature, and kind of
Hmm.
once we kind of go through that because maybe it will answer some of your questions,
Yeah.
before, and then if we have time at the end, then we'll move on to that. Um, does
So
this?
you saw the picture, right,
I did. Yeah, I
from this morning?
downloaded it. I
Yeah, yeah.
downloaded it
Okay, good.
actually, so we
Okay,
can
cool.
even share it on this.
Yep.
Okay, so
Hmm.
so we're here today to discuss um, temperature, and which is one of the 18 dimensions of motion from Walter Russell's concept. I have a couple pictures for you. I really like this. Like, I think this will be good for people to, um, because temperature is something that everyone's kind of familiar with. When it's hot, when it's cold, and so anyway, I'm just going to jump right in. So I'm going to start with reading some from the Universal One, and I have some pictures as well. Now let's see here. So this is a graphic from the Universal One. For those that are interested, it's called the Universal Seesaw, and it is definitely significant to Russell's concept of dimensions. So you notice in this picture, I want to point your attention to the balls that are labeled C. They're on this, seesaw, if you will. They're of equal mass, equal pressure, and they're balanced on this fulcrum, of the seesaw, right? Equal. So as we look, the direction there, he's got these arrows. So one says the direction of expansion toward disappearance is headed this way to the top. And the other arrow is the direction of contraction toward appearance, and it heads down here to A. So he says that, every sphere of equal mass, every sphere is of equal mass. Any change of potential in mass changes all of its dimensions, and its position also changes to conform. The constant of energy for the mass does not change as the dimensions change. The lifting power of an expanding mass at D equals the compression capacity of a contracting mass at B. And all dimensions change in universal ratios. Okay, so this is where he's kind of describing, this is just, describing that all the dimensions, all these 18 dimensions we talk about, they are essentially because of a two-way system of Russell's concept, gravitation versus radiation, expansion versus contraction. Every bit of matter in the universe has both of these forces acting on it at the same time. Okay. They are just more preponderantly, contractive or more preponderantly expansive, except at the apex of at the amplitude of the wave, then they're exactly equal, and where that mass would be a perfect circle. So so just keep this in mind because we're going to talk about temperature, and we're going to show kind of how this is relevant. For those who are interested, this is on Universal One, page 193, in the hard copy. So this is expressions of gravitation and radiation, temperature, the eighth dimension. This universe of more or less is a universe of varying pressures. Temperature is a dimension of relative and opposing pressures as expressed in its opposites, heat and cold. The popular concept that temperature measures only the degree of heat is not in conformity with the laws of motion. Heat is improperly presumed to be an effect of motion which is operative in both directions. In other words, that which we call cold is assumed to be less heat. This idea must be eliminated from man's thinking. Heat and cold are as much the opposites of temperature dimension as positive and negative electricity. Contraction pressure and expansion pressure, are opposites um, of other dimensions. So every dimension must have its opposite expressions which persist in the opposition. Each of these are not relatively less or more of the other. Like deceleration is not less acceleration. It is the result of the expression of one force, just as acceleration is the result of the expression of its opposite. Neither is negative electricity less positive electricity. Neither is the blue end of the spectrum, less of the red end of the spectrum. It is as inaccurate to describe cold as less heat as to describe blue as less red, or to describe negative discharge as less positive charge. So the cold expansion pressure, radiation, the blue half of the spectrum, and negative electricity are the evidences of the domination of one of the two opposing forces, every expression of which is in an opposite direction from that in which heat, contraction pressure, generation, the red half of the spectrum, and positive electricity are expressed. The greater the contraction of charging bodies, the more heat a body will register from generation. And conversely, the greater the expansion of discharging bodies, the more cold a body will register from radiation. He's pretty clear there that heat and cold are two different are the results of two different forces, the gravitative compression force versus the radiative expansive force, and those work on all matter, and they're just preponderantly preponderantly more gravitative or preponderantly more radiative. I do want to read this. Okay. Contraction of volume by integration of the same mass into lesser space is resisted by expansion pressure. Resistance to contraction heats by the opposition of the opposing forces. Heating bodies approach each other and recede from cooling bodies. So those are the two opposites, right? Heating bodies come together. He says, like attracts like. And those heating bodies that are contracting, they're going to, run away from or be repelled from cooling bodies. Expansion of volume by disintegration into greater space is assisted by the expulsive force of contraction pressure. What he means by that, like as the pressure is contracting something, it's also pushing expansion outward. The more contraction pressure you have, the more expansion pressure you're going to have. And so the converse of what he said about heating bodies, expanding bodies recede from expanding and from contracting bodies. If this law of motion is well founded, then cooling bodies, expanding bodies, and the repulsion of radiation must be related. Expanding bodies cool. Expansion of volume repels. Cooling bodies recede from cooling and from heating bodies. Expanding bodies seek lower pressure equilibriums. All right, this is worth saying. So, accelerated motion being simply due to the decreased volume of a changed potential position does not alter the constant of energy which produces that motion. The higher temperature of a decreased volume does not mean more heat than the lower temperature of the larger volume of an equal mass. So that was kind of what he showed on that seesaw. There, all of those things on the seesaw were of equal mass, but they were just at different potential positions. One was vastly expanded in volume, so therefore lower potential. The other ones, were greatly contracted and therefore higher potential, and in a different position, because when the potential changes, the position will also change. So here's something kind of interesting. The state of motion which produces incandescence is one in which the directions of the opposing forces are directly south and north across the pressure zones, which define the orbits of floating bodies. Ooh, I shouldn't have read that because that's that's a little bit more advanced. We haven't talked about pressures yet. Like as I said before, just in general, when I read from directly from a book, I'm not going to read the whole thing. Like, I want, people need to go out and read these books and contemplate them themselves. But I'm trying to pull out some of the things just to make you guys think about this. So he starts talking about kind of temperature and how they affect the elements um, and the planets.
Have you got a diagram we could look at while you
Let's see.
read it?
Well, actually, this is, let me go ahead and share my screen. So first there's this diagram, which we talked about. And what I want to kind of bring to your attention in terms of temperature. So we would say that the mass at sea and the mass that's balanced on the other side of the seesaw at sea, those would both be the same, equal mass and equal potential, and they would be the same temperature. Okay. Now, as that expands and goes to D and expands more and goes to E, the temperature would lower. Okay. As the volume increases, it would lower. But that big ball at the top that's labeled E, that has the same mass as that's labeled C, but the temperature is different, the potential is different, and therefore its position is different. Now, conversely, as C would contract to B and to A, the volume would be different and would therefore be a higher temperature because all that matter has been compacted together. And therefore, once again, still the same mass, but a higher potential, so hotter, and therefore it's in a different position. So this seesaw is relevant to every single dimension. This is how the dimensions shift and change. And as you learn each dimension, you'll see how they're connected to every other dimension. We recently, beforehand, we talked about time and how there would be speed time and power time. So in this example, as C as C expands up to E, now it's a big, huge ball, the speed time would be increased and the power time would be decreased. And you guys can go back and, listen to our time video to understand that. And conversely, as it goes towards A, the power time would increase and the speed time would decrease. So that's why Mercury, the planet Mercury, is more like this little ball A, which is close to the sun and high potential and very hot. Whereas if you go further out and expand it all the way to E, then that's like the gas giants that are way out, away from the sun. Their temperature is much lower. Their volume is much bigger and their potential is much lower. So let me switch to another diagram here. Oh, he really goes into a lot of detail here, but let me pull out one example. Let's see. Okay, so it does not require much imagination to visualize a condition of relative heat on the planet Neptune when one considers that hydrogen freezes into a rigid solid in the ordinary temperature of Neptune, whereas on this planet, its freezing point is negative 250 degrees Celsius. So that is because we are much higher potential than Neptune is. We are much closer to the sun, which is the gravitative primary of our solar system. So therefore, we're higher potential and we're hotter. Whereas Neptune is way out there, much lower potential, much more expanded, and therefore much colder. So when we look at, say, one element like hydrogen, if we look at hydrogen here, well, every element has its melting point, its freezing point, or its boiling point. And so, right, for hydrogen to freeze on our planet, we got to send it down to negative 250 degrees Celsius. But out there on Neptune, hydrogen would just be found as like a solid because Neptune is so cold. And on that, it'd have to be heated greatly in order to get back from its solid point to a liquid or a gas. Conversely, frail substances to us would be would become the staunchest of building materials to the possible inhabitants of Saturn or Uranus. On this planet, we should not dream of building our houses of ice below the Arctic Circle, right? We fail to realize, however, that our staunch houses of stone and iron are but the ices of those substances. The only difference being that the melting points of ices with which we build are so much higher than the normal temperature of this planet that they are to us as dependable solids as the ice of water is to the Eskimo, like building an igloo, right? But all of our dependable solids are but the ices of various substances of varying states of dependability. Their dependability being conditioned by their own separate locked potential positions. So I bring up the periodic table here because he starts talking about, elements. All right, so we've got our periodic table here. We've got it, it's separated into octaves, first octave, second, third. But okay, so you see the first, second, third octaves. Here's the fifth octave, fourth octave. So he talks about by studying the table of the elements, one will see that the melting point of the inert gas at the beginning of the fifth octave, which is helium, we will see that the melting point at the beginning of the fifth octave is negative 271 degrees Celsius, whereas the melting point of the substance in the first tone, and let's see, the first tone being lithium, is plus 180 degrees Celsius. So that of the second tone is 1280 degrees. That's beryllium. Then it goes boron, which is 2350 degrees. And finally, at the double tone of carbon, which is at the amplitude of the wave, the melting point is a whopping 3600 degrees Celsius. Going back down the negative side of the scale, the melting point of the substance in the third tone is negative 210. That would be nitrogen. The substance in the next one would be 218. And then the first would be 233. Sorry, essentially, but you can see the pattern. So he has one comment about the midtones, which we find later down in the higher octaves. Okay. Those tones are in between the true tones. And so there's some weirdness going on. He just comments and says that, he just comments and says there are some irregularities of the midtones that don't follow exactly like the temperature kind of going up in a orderly manner that you would be used to like all of the other full tone positions. But he comments and says that this does not mean that the midtonal irregularities are exceptions to the law. It simply means that midtones are split tones, and the totals of all dimensions of all the split tones in any octave are the constant of the double tone of that octave. We will have to go more into that, I think, when we talk more about the periodic table. But so yeah, in temperature, as in all other dimensions, the variation of heat, which gives us what we call higher temperature, is merely a preponderance of heat at the expense of its opposite dimension, cold. The constant of energy in all of its expressions is equal in every tone of every octave, the midtones between each tone counting as one tone. So all variations of temperature are therefore but variations of the opposites of dimension, heat and cold, gravitation and radiation. All variations of dimension are orderly and in universal ratios. Now, we'll get to universal ratios when we start talking about universal mathematics. That's like after we've done all the dimensions. Yeah, and this is worth saying too. The relative temperatures of the planets of the solar system are as much in conformity with the universal ratios upon which the formula of the Locke potentials is based as the temperatures of the various elements are in conformity with their law. Without the variation of temperature in systems and the masses of systems, nature could not produce her effects of form. She makes no variation in one opposite of any system without balancing the variation of the opposite dimension of an opposite system. So I think I want to stop right there for now and just kind of, generally kind of discuss kind of what he's saying here. Um, he's really showing us in this dimension of temperature, as in all dimensions, as in all 18 dimensions, that it's really about two forces. And in terms of temperature, it's heat and cold. So, we look at like a thermometer and we say, oh, it's this hot. But in Russell's concept, we could also say it's this cold. And because it's really both heat and cold fighting against each other, just one being more preponderant than the other. So that is just, and that's where that seesaw, it really, that idea is key to Walter's concepts because everything is a two-way, two forces working against each other through the whole entire life cycle of whether it's a planet or a person or an atom or, of an element. There's always those two forces battling each other and running that life cycle of more preponderance of one, then coming to equilibrium at the amplitude or the maturity point, and then the one that was less preponderant now becomes more preponderant, and it goes back until we get to death. So that's the life cycle, and as it goes through its whole life cycle, all of the dimensions are preponderantly contractive at first, then they reach an equilibrium of those two forces, and then they become preponderantly expansive as they expand to, what we could say is death of their life cycle. So that is, and we talked about this with weight, how there's a positive and negative weight. So we're talking about this with temperature, how there's essentially I guess you could say a positive and negative temperature. I mean, it's heat and cold are the two forces that are going against each other. Let's see. I think that's basically it because he really kind of goes into more about the melting points of various elements. So I'm curious what you think about this, Kirsty, or if you have any questions.
Yeah, it's all very balanced and orderly when you listen to how Walter has written it down.
Right.
And
Right.
then you look out into the world and it is very confusing. There's the
Yes.
complexity.
Yes.
Yeah.
And
Yeah,
that really oh, go ahead.
mm,
Oh,
I
okay.
see that both ends of the polarity are valid and they are not any less of the other. They are two very valid
They're battling each other the
scales.
whole
Yeah.
time. Right. And just one is more
Mm.
preponderant than the other. For those of you, it just means like there's more of one and less of the other as it's changing through its life cycle. But it always balances out, you know, um, such that if there's more of one, then eventually that one will become the less one, and the other one that was less becomes the more one, you know. The first shall be last, and the last shall be first, something like that. Um, this is one of the pictures from when in the universal mathematics chapter, and this is describing the universal ratios. And this is like my probably my favorite, picture in the whole book. I don't know, this or the periodic table. No, I think I like this one. But, I got a t-shirt of this, I literally sell these t-shirts. But like this is the universal mathematics ratios that this is the way that we'll be able to calculate all of the dimensions of motions in their expansion dimension and their contraction dimension, which are always together. So, when we get to that, it'll be, I think, pretty fascinating. I think that's a good start on temperature. I think I'm gonna kind of leave that there. There are a few other things that we wanted to talk about. Does the relationship of hot and cold for you, Kirsty, do you see how it integrates with the other dimensions that we have talked about, like expansion and contraction, and
Hmm.
speed time and power time, potential. It's and for those, I'll just say it one more time, just to, the connection here is temperature is affected by when there's a mass, if the mass contracts and gets smaller and smaller, and that mass is put into a smaller volume, it is going to heat up, and it is going to be a higher potential, and it's going to move its position. Well, it's going to search for a higher potential surrounding. The other side of that coin, if you will, if there's a mass and it is expanding, it's an expanding body, it is spreading out the mass into a larger volume, and therefore it will be getting colder. Okay, and it will be lower potential, and therefore it will move away. Okay, and we are back. So I did want to read one more section, just kind of, I feel like this is a good overview um, for temperature. So, Walter says, thus is nature repetitive in all her states of motion by her method of conducting all her opposing dimensions in cycles. The temperature of the universe is constant. Any variation of the constant is but a multiplication or division of that constant in direct or inverse universal ratios common to the variations of all dimensions according to whether the dimension is an expansion or a contraction pressure dimension. So um, he kind of sums that up there. And just to kind of, as another kind of sum up here, the idea conveyed by the word heat developed or energy developed or energy generated, wherein a heretofore presumably non existent heat or energy is supposed to be developed, is not in accord with the laws of motion. Accelerated motion being simply due to the decreased volume of a changed potential position does not alter the constant of energy which produced that motion. The higher temperature of a decreased volume does not mean more heat than the lower temperature of the larger volume of an equal mass. It means that the same constant of heat has readjusted itself to the changed potential position in accordance with the 19th law of motion. The constant of heat energy is the same for both volumes and both masses. Any force of the universe of dimension is an opposing pressure force. The pressure force, which compresses great volume into little volume and registers The intensity of that compression in heat is the male electropositive generoactive electric force of inhalation. Inhalation is an endothermic force. That means that it is heat absorbing in the commonly accepted scientific sense. Heat absorbing in the true sense means gathering together the potential of resistance from large area and compacting it into small area of the same constant. The state of motion which produces incandescence is one in which the directions of the opposing forces are directly south and north across the pressure zones which define the orbits of floating bodies. So I wanted to read, that part again because he really kind of sums that up in terms of temperature and kind of how it's related to our gravitation and radiation forces, and kind of our some of our other dimensions there. Let's see. Let's stop the share because Kirsty made another diagram for us. And I'm going to pull it up just so that it's here on this Zoom meeting. We have shared that just so you guys can take a look. First, I'll zoom in kind of on the top here. There's a Walter Russell quote for you guys to read. I do think I want to go over this when Kirsty is on the call since she made this, and but I just wanted to kind of give you a kind of a quick visual in case you guys wanted to study it on your own for next time. Okay. So I don't know. I'm not I did not read it myself in thorough, because I wanted to wait for her to be on here. So, I can't vouch for anything that is said on there yet because I haven't read it yet, but we'll this is just so that you guys kind of see it and can maybe study it a little bit before our next Zoom meeting. Because then we'll discuss it later because this is essentially one of her questions. But since she's not here, we will move forward. Okay, so well, we essentially went over the expressions of gravitation and radiation in terms of the eighth dimension temperature. I think that, let's see, let me give this how much time we have left here. I think maybe Kirsty's not coming back. And I think because today I am feeling under the weather, I think I might end the Zoom here. I'm going to look and see if there's anything other that's relevant that maybe I should add to this Zoom. So bear with me 1 second. Actually, I'm going to share my screen one more time. This diagram one more time. Because there was oh, right, there's a little bottom part. So this is the universal seesaw. We didn't read this down here at the bottom. It says every mass finds its own position according to its ability to displace other mass. A mass of great volume must seek a lower potential position than that required by an equal mass of small volume. Okay, so good. I'm glad I got that on there. Yeah, and like this is this, studying this and understanding this kind of cycle, or rather this kind of relationship of volume and potential and position, this is significant for all of Walter Russell's 18 dimensions. And any of his 18 dimensions, we can talk about them in this way because as you see, there's one arrow going towards expansion and there's another arrow going towards contraction, which are always opposite of each other. And so any dimension, that we talk about, we can talk about it in terms of it expanding or in terms of it contracting. Okay, so I like to say, there's 18 dimensions of motion, but there's really 36 of them because it's double, because each dimension of motion, like temperature, has two forces working against each other. in terms of temperature. Obviously, it's hot and cold. So, I mean, that one's like really obvious, but some of the other ones, like time, not so obvious with speed time versus power time. Um, volume is pretty obvious. Larger volume is lower potential and cooler. Um, Smaller volume is higher potential and hotter. And those bodies, this is another significant thing about Walter's concept that I do want to repeat for you guys. And that is, every bit of matter or mass um, is either contracting or expanding. I mean, except for the one quick moment when it's at the amplitude of the wave, then it's an equilibrium there. But it quickly continues past that and continues along its life cycle, and it becomes imbalanced again. And when the expansion will be more preponderant than the contraction, because we can do that for all the dimensions. Let me just generally say to repeat how matter moves regarding whether it's expanding or contracting. Okay. So he's very clear that matter that is contracting, it's preponderantly gravitative, preponderantly contracting, preponderantly rising in its potential. If you have two of those near each other, they are going to attract each other. Now, the opposite of that is if you have a body that is expanding, it's preponderantly radiative, preponderantly expanding, it's getting larger in volume, and it is getting lower in potential. If you have two of those items or masses, they will repel against each other. Okay. And there's one more situation. Well, what do the repelling, expanding masses do when they see a contracting mass? They will repel. Okay. So it's a little counterintuitive. You might think that, oh, contracting mass will, opposites attract or whatever. Russell's very clear. Nope. In this case, like attracts like, and dislike repels dislike, and repels like in terms of expansion. I think that is actually, in my opinion, could be one of the reasons that we see the universe expanding in traditional science. Because as stars that we see, obviously stars have already been contracting. They've brought together a large amount of volume of light and matter into a much smaller volume. So they become super high potential, and um, and then they could be past and it depends on where they are in their cycle. But if they're past their amplitude point, then they are radiating. And radiating stars will repel other radiating stars and will repel other contracting stars. So that means like all the stars are expanding away, are pushing, like actively pushing, so away, repelling from each other. And so therefore, that is a constant force that's going to cause the speed to increase. Now, yes, Walter said if they're two contracting suns, then they would attract each other. Okay. So in this case, preponderantly contracting is like, and they will attract each other. Preponderantly expanding will repel each other and will repel the opposite, contracting bodies. Okay. So I think that is just, another kind of way for you guys to think about how the universe works and how matter moves around. It's always because of these two forces. The stronger the forces, the higher potential and higher pressure that things are. I should say, the stronger the opposition of the two forces means higher potential and smaller volume. The lesser opposition will mean more expanded volume and lower potential. So that's just kind of a way to think about, you know, to kind of integrate that into how things move. I think, guys, I think that's going to be it for me today. But we did cover all of temperature. We covered kind of how it relates to other dimensions, and very importantly, we covered how all the dimensions use the universal seesaw. So, check out that diagram to try to, contemplate over things. It's been great. It's been a pleasure as usual. Have a good night and thanks for listening. And we'll hopefully see you in the next one.